Man has inhabited the surface of the Earth for hundreds of thousands of years. In a miraculous way, he has always been able to survive. All around him, he has found hostile forces that could snuff him out in an instant, from the very door of his primitive home to the far reaches of outer space, laced with various forms of deadly radiation. Scientists, the curious men of the human race, have puzzled over the mysteries of the Earth and the stars. They have gained much knowledge of the Earth's crust. Sometimes they have understood a few of the terrible and exciting truths about the forces that surround them, above and below. They've tried to use their new knowledge for man's benefit. Some materials of the Earth's crust are found in profuse quantity. Others may be rare. Only since 1797, in our era, have scientists understood that one of the rarest materials in the Earth's crust, diamond, is simply another form of a very common material, carbon. In the dim past, when the Earth was formed, molten material from inside was tossed upward through cracks in the Earth's crust, called pipes. After diamond was formed deep within the Earth by an unknown process, the pipes carried it to the surface. At the top of such ancient pipes, or in debris from their erosion, man finds diamonds in India, in Africa, and in South America. When scientists understood that the rare diamond is only another form of carbon, they tried to make diamond from carbon by many processes. They constructed strange furnaces, some involving high temperatures, others involving high pressures, still others involving chemical transformations. They shot a high-powered bullet into a tiny hole at a range of 6 inches to achieve heat and compression. They tried mixtures of various chemicals, but they failed. In 1954 came a landmark in man's search for knowledge about his world. Scientists of the General Electric Company in the United States produced man-made diamond for the first time. The starting material for man-made diamond was graphite, with its carbon atoms tightly bound in planes, but with comparatively weak atomic forces holding the planes together. The task was to squeeze the same carbon atoms together into the more compact atomic arrangement of diamond, and to hold the unstable crystals in the diamond form. The scientists studied various processes, built new pressure chambers, and began to experiment with various temperatures and pressures, high and low. Eventually, a pressure and temperature map was drawn that showed the region in which diamond crystals could probably be grown. The next and most difficult challenge was to achieve in the laboratory the forces indicated by the map. Ultimately, the scientists designed a pressure chamber that could achieve pressures equal to 70 kilobars, representing a depth in the Earth of nearly 150 miles. Unlike their predecessors, they learned to hold the pressures for a long time at high temperatures. The 2 pistons compress a sample placed inside the donut-shaped chamber. Now, the secret of the squeeze is not in the power of the press, but in capturing this power in the pressure chamber. As the pistons press together, the donut-shaped chamber supports their force. Now, the press can supply the pressure. But how to apply heat? The answer? An unusual furnace, only 2 centimeters long, using the heat of electricity to produce the required high temperatures. An electrical current passes from one piston through the tiny furnace bearing the graphite to the other piston, creating the white-hot temperatures needed with the pressure for the diamond transition. Components fit compactly into a cylindrical holder containing the tiny furnace. But a catalyst is needed to speed the transition. Small metal discs alternate with graphite discs in a graphite-lined metal tube. The graphite discs are the starting material from which the diamonds can be grown. All the discs are in place. The sample is fitted into the holder containing the furnace. The carbon tube furnace, the end of which appears as this black ring, conducts an electric current to heat the sample inside. A disc to carry electric current to the small furnace is placed on the end of the holder. The sample and lower gaskets are placed on the lower piston. The piston rises and lifts the sample up into the belt. As pressure forces the pistons together, the sample and its carbon atoms are strongly compressed. The force builds up and up and up, eventually reaching nearly 500 tons, almost 1 million pounds per square inch. Electric current then is applied to heat the sample. The outer surfaces reach 750 degrees Fahrenheit. Inside, 2,600 degrees Fahrenheit. It melts the metal catalyst discs. The carbon reacts with the metal catalyst discs. Its structure begins to change. This is the region where diamond grows. The crystals grow. Thin films of the molten catalyst metal migrate through the graphite to help change it to diamond. After the proper time, the diamond transformation is complete. Then, the temperature and pressure are slowly lowered. Mining of man-made diamonds begins. The gasket and holder are fragmented from the intense pressures. The metal cylinder containing the diamond is intact. The tube is sawed open. Tiny diamond crystals glitter in the light. A concentrated bath of sulfuric acid and potassium nitrate removes graphite but does not affect the diamond. Leaving the crystals clinging to what is left of the metal discs. Some still have a small amount of graphite clinging to their outer surfaces. Most of the diamonds on the discs are coated with a thin metal film, but on a few of them, the metal skin has come off. The metal discs are dissolved in nitric acid, producing dark vapors of nitric oxide. The glittering sediment is separated from its surroundings and is washed in distilled water to remove any acid residues. The physical appearance of these crystals was the first clue in 1954 that man had finally learned how to grow diamonds. For scientists, always doubters, many tests were required to confirm the diamond transition. First, they determined the crystals would scratch natural diamond. Good. But scientists had to know two more things. First, that they are a form of carbon. The crystal burns and forms carbon dioxide. Excellent. Then, they must test to make sure the crystals are identical in structure to natural diamonds. In an X-ray diffraction test, a crystal is subjected to an intense beam of X-rays. The X-rays are deflected by the crystal in certain characteristic directions and are recorded on photographic film lining the inside of the container. In this way, the crystal's unique fingerprint is exposed. X-ray diffraction tests can be conclusive evidence that man-made diamonds are identical to natural diamonds. As no two fingerprints are alike, no two X-ray diffraction patterns of thousands of materials are alike. With all tests completed, On February 15th, 1955, after 4 years of intensive work by a team of scientists on the Diamond Research Project, synthesis of man-made diamond was announced. This success in duplicating nature's hardest material gave man a new source of industrial diamond, absolutely vital to industrial production, for tools, for drilling, cutting, grinding, polishing. Today, new methods of creating diamonds are being perfected. Discovery of man-made diamond marked a major achievement in man's search for certainty in an ever-changing world. As they look beyond present attainable pressures and temperatures, tantalizing questions remain. Are there harder forms of carbon than diamond? If we subject carbon to higher temperatures and pressures, will we find materials even more valuable to mankind? What lies beyond? As in all scientific research, a solution raises even more questions. And scientists continue the never-ending search, not only to satisfy their own curiosity, but to gain the better life their answers can give all men.